Hello everyone, my name is Hamad Rehman and I'm a PhD candidate at Delft University of Technology. In this paper, an innovative design methodology is proposed. It employs a gradient-based optimizer to simultaneously optimize the size, layout, and number of internal structure components of a wing box, including the spars, ribs, and stringers. The proposed method can be used to tailor the bend-twist coupling of a wing to achieve superior designs with the desired static and dynamic aeroelastic response. In this paper, the proposed method is used to design a stiffened panel subjected to buckling constraints. Stiffened panels are widely used in aircraft to build the structure of wings and fuselage. Since it is a thin-walled structure, therefore, besides strength failure, it is prone to fail under buckling instability. Considering the requirements related to performance, safety, and economy, optimization methods are generally employed to minimize the mass of a stiffened panel while tailoring its stiffness to achieve the desired design response. One such method is topology optimization, which is used to determine the optimal material distribution within the design space. It is best suited for design problem where the initial configuration is not known. Therefore, a design domain discretized with 3D elements is generally used as an initial design for topology optimization. During the optimization, the elements which do not contribute to the stiffening of the structure are removed. In this way, the greatest design freedom is ensured, but at a very high computational cost. In 2017, topology optimization of CRM wing was performed using 1.1 billion solid elements. It took 5 days of computing time on 8,000 CPUs, even though only the stiffness was considered for optimization under 3 linear static loads. Buckling analysis is time intensive. Therefore, to perform the topology optimization of a thin-walled structure, the efficient approach is to discretize the design domain with 2D plate or shell elements. The initial configuration in this case is generally fixed. Though this approach yielded a significant change in mass, but the resulting design can be costly to manufacture. The flowchart of the proposed methodology is shown. Here, the three key aspects are highlighted. CAD-based parameterization offers two advantages. Firstly, the geometric constraint to avoid overlapping and crossing of structure members are implicitly applied through the layout parameterization scheme. Therefore, no additional constraints on the grid point coordinates are required. Secondly, the CAD model is maintained throughout the optimization process because the CAD parameters are directly controlled by the optimizer. Therefore, the additional step of converting the optimal design back to CAD is not required. The analytical response sensitivities require less computational cost and are more accurate than the finite difference method. The gradient-based optimizer allows a large number of design variables, hence a greater design space can be explored. The proposed method is used to design a stiffened panel with 7 blade stiffeners. The bottom edge of the panel is fixed and the shear load is applied on the top edge. The size design space is parameterized with 8 design variables to optimize the thicknesses of skin and stiffeners. The number of stiffeners is parameterized by assigning a topology design variable to each stiffener. This variable can vary between 0 and 1 and is used to calculate the properties of the artificial material assigned to that stiffener. During the optimization, if this variable becomes 0, then the contribution of that stiffener in determining the mass and stiffness of the panel is lost. It is considered an inactive or ghost stiffener. The stiffener is considered fully active when this variable becomes 1. The layout of a stiffened panel is parameterized using a CAD-based parameterization. The CAD model is generated in such a way that the location and orientation of each stiffener are controlled with only two CAD parameters. As shown here, the location of point x1 and x2 are defined as the layout variable for stiffener 1. Similarly, location of points y1 and y2 are defined as the layout variable for stiffener 2. Using this CAD-based parameterization, the issues like overlapping and crossing of stiffeners are avoided. This parameterization scheme is very effective because a greater design freedom is achieved through a limited number of design variables. The optimization problem is to minimize mass of the stiffened panel subjected to buckling constraints. Additional penalization constraints are defined in order to force the topology variables to the limit values of 0 and 1. The results of the simultaneous size and topology optimization are shown. The mass of size optimal design is about 21% lower than the initial design mass. The mass of the simultaneous size and topology optimal design is about 27% lower than the initial design mass. A greater mass saving is achieved in the latter because of presence of two ghost stiffeners in the optimal design. The optimal mass can be sensitive to the initial design. Therefore, additional investigations are conducted using the designs with different values of topology variables and the penalization factor. It is observed that the penalization factor strongly influences the number of ghost stiffeners in the optimal design. When penalization factor is 2, the number of ghost stiffeners is greater than the number of stiffeners, therefore a heavier optimal design is found. When penalization factor is 5, there are no ghost stiffeners in the optimal design. Therefore, the optimal mass in this case is the same as achieved through the size optimization. A similar trend is observed when the number of stiffeners are changed in the initial design. The lowest optimal mass is achieved while using 9 stiffeners and the penalization factor of 4. When penalization factor is 5, there are no ghost stiffeners in the optimal design. It can be concluded from these results that while using a penalization factor of either 3 or 4, a lower optimal mass is attained in comparison to the same achieved through the size optimization. The results of simultaneous size and layout optimization are shown. The trend herein observed is that the thicknesses of skin and stiffeners are reduced to their lower bounds. The stiffness of the panel is tailored predominantly by the movements of stiffeners towards the right side of the skin at the bottom edge. It can be concluded from the results presented here that the buckling response of the stiffened panel is more sensitive to its layout design variable in comparison to the size design variable when optimized simultaneously. The results of simultaneous size, layout, and topology optimization while using a penalization factor of 3 are shown. It can be observed that the thicknesses of the skin and stiffeners are reduced to their lower bounds. The stiffeners at the bottom edge of the skin are shifted towards the right end to meet the buckling constraint. The first stiffener from the left side of the panel becomes a ghost stiffener, and this generated a loss of stiffness which is compensated purely through the change of layout. Therefore, it can be concluded that when size, layout, and topology variables are optimized simultaneously, the layout variable dominates the optimal design. The result summary is shown here. It can be concluded that the lowest optimal mass is achieved through the simultaneous size, layout, and topology optimization while using a penalization factor of 3. In comparison to the initial design, a mass reduction of about 51% is achieved. This reinforces our previous conclusion that the lower optimal mass can be ensured while using a penalization factor of either 3 or 4. Conclusions. The proposed methodology successfully performs simultaneous size, layout, and topology optimization. This provides additional capability to locally tailor the structure. The buckling response of the stiffened panel is found more sensitive to the layout design variable in comparison to the size and topology design variable when optimized simultaneously. CAD-based parameterization allows the use of CAD models, which is crucial for the wider adoption of this method in industry. The novel design achieved through optimization can be easily manufactured without additional cost penalty. The proposed methodology is not limited to the stiffened panels only and can be used for the design of complex configurations such as a wing box or other thin-walled structures. Thank you for your kind attention.